Hey students, this is the key to quiz 5. Find the maximum value. So we need to check f at 0 and 4 because those are the endpoints. Put 0 in, you get 0. If you put 4 in, you get 16 over e to the 4. So what is that? So that's 0.29 basically. But then we also have to see if there's any critical points in that interval. So the derivative, since that's a product, we have to use the product rule. So it's the derivative of the first times the second, and then the first times the derivative of the second. So an e to the negative x and an x can factor out of this. So I'm just going to write, instead of e to the negative x, I'm just going to write it like that. And then what would be left? A 2 minus an x. Okay, so either x, so if this is 0, which is what we want to have an extreme value happen, one possibility is that x is 2 and the other is that x is 0. And we've already got the x is 0 thing done, so we just need to do f of 2. So that would be 4 over e squared. Which is 0.54. So this one wins. That's your absolute maximum of this function over that interval. Find the equation of the tangent line to f when x is 1. Well, okay. What we need to do is just put 1 in here. So, right, so this is your slope. Your slope occurs when your derivative is 1 in this case. You'd set your derivative. So that would be 1 over e times 2 minus 1, which is 1 over e. So that's your slope. So what would your value be at 1? What is f of 1? It would be 1 squared e to the negative 1, e to the negative 1, which is 1 over e. So both the derivative and the main function took on the same value there. So your tangent line would be y minus y naught equals slope x minus x naught. So if you distribute that, and you just add this, you end up getting y equals 1 over e x. So it's a line with slope 1 over e through the origin. Alright, if we differentiate this, but before we do that, let's simplify y here a little bit. So when you have logarithm to a power, the power can come out back of the logarithm. Okay. And one of the properties of absolute values is that you can just kind of distribute them over a product or quotient. And then one of the properties of logarithms is that the log of a quotient is the difference of the logs. So this is another way of writing y. So then y prime would be constant multiple. And the derivative of a logarithm, log absolute, is 1 over. So it's just this thing down in the denominator times its derivative by the chain rule would be 3x squared. The derivative of that's just 1 over x. So that's the answer to that. Okay. So Mount Pleasant has a 2,000 population of 2,500 inhabitants. The city's population doubles every 50 years. A politician wants to cap it at 800,000. Okay, so A naught is the initial value of this exponential function, which they said was 25,000. That's the starting population. Okay, so and then the doubling time means that you'll have a population double that in 50 years. So we make t equal to 50. So dividing, you get 2. Then you take the natural log to strip off the exponent, and then so k is 50 over, or I'm sorry, it's natural log of 2 over 50. So let's get that number roughly. So that's approximately 0.013863. So the model then is A of t is 25,000 e to the 0.013863 t. That's the model that we would use exponentially. Okay. Now, in a logistics model, so in an exponential model, you know the initial value first. But in this one, you know m first. That's the capping value. Okay, it's like the horizontal asymptote. The thing is approaching the supreme law of the function. Okay. Now, we know that a of 0 has to be 2,500. So we know a of 0, 25,000, right? But that's also equal to 800,000 over 1 plus c, because this thing is exponent 0 means that's a 1. So if I multiply by 1 plus c and divide by 25,000, I get that c is 800,000 divided by 25,000 minus 1. So 800 divided by 25. That's 3,200 divided by 100. So 32 minus 1 is 31. So C is 31. Okay. Now we need to use the fact that A of 50 is 50,000. Doubles the initial value. So that would be 800,000 now over 1 plus 31 e to the negative 50k. So now we need to find that k. So I'm going to multiply by that and divide by that. So I get 1 plus 31 e to the negative 50k is 800,000 divided by 50,000. Which is 800 divided by 50, which is 80 over 5, which is 160 over 10, which is 16. So 31 e to the negative 50k equals 15. So e to the negative 50k is 15 over 31. So negative 50k is natural log of 15 over 31. So k is natural log of 15 over 31 divided by negative 50. So let's get that. So I'm getting 0.014519. Okay, that's 5 significant digits. So now we can get our model. It would be A of t is 800,000 divided by 1 plus 31 e to the negative 0.014519t. Okay, and you can do a quick graph check to see if you did this right. So I'm going to compare that model to the other one. So you can just put these in here. Okay, that model is that, and then the other one is 800,000 divided by 1 plus 31e to the negative 0.014519, and then x again. Okay, now the window, you need to have like a y max of 800,000. I'll make it 1,000,000. And then since it doubled in 50 years, I'm going to go out to like 500 years just to see this thing spread itself out. So I'm going to go from time 0 to time about, I don't know, maybe 400 years out. So I'll scale that by 50 so we can see a doubling time. And then the population was way down there at 25,000, so I'll say a minimum population of 0 and a maximum of 1,000,000. So that's 10 to the 6th power. So since I scaled by, so since I have a delta y of 1,000,000 there, I guess I'll scale it by 200,000. So now if I graph that, I should see first the exponential, then the logistic. So that's the exponential model. The logistic should look similar to it at first if I did it right. Yeah. And then it just kind of starts tapering off. So I'm pretty happy with that. So now that we know that those are correct, it says compare the population growth rates in the year 2100 of both models. Okay, so we have to differentiate these things and calculate the derivative at the year 2100, which would be right here. Right, so their answer is going to be quite similar. You know what, now that I can see that the answers are almost going to be the same, I think I would rather choose a different number. So on your version of this, it's going to not be 2100. I'm going to make it, so this is 2000, 2050, 2100. This is the year 2200. So I'm going to do it there because that, you can clearly see that the tangent line here is different from the tangent line here. Okay, so that's what I'm going to do. So yours will say 2200 on it. Okay, so we need to get their derivatives now. So if we looked at this model here, you just multiply this by the exponent. So I'm going to multiply by this k right here. So 0.013863 times 25,000 e to the 0.013863 t. That's the derivative of the exponential model. Okay, so if we evaluate that at 2200, we should get, let me think, let's see what we would do. It looks like if I go about 100 years, I'm going to increase if I go 100 years, it looks like I'm going to go from here to about here. So that's 600,000 per 100 years. So I think I should get an answer of 6,000 here if I do this, just looking at it graphically. So let's see, you do k times initial population, and then e 0.013863 times 2200. I'm hoping to get an answer of around 6,000 if I did that correctly. Whoa, that is a truly massive number. Right. Wow. That doesn't make any sense at all. Oh, 0 is 2,000. That's what the problem is. Yeah, so this is still 2,200, but I needed to put 200 in there, not 2,200. Sorry about that, because that's 200 years after 2,000. So that would help if I didn't have this 2 here. There you go. I knew it needed to be about 6,000. I was super confused about that. Okay, so it's 55, 45. Okay, so people per year, new people per year. That's growing very rapidly. That's a lot of people to come join the town in 1 year. That's insanity. So this one's going to give us a more reasonable number. Let's see if we can guess what it will be. So this is 2,100 to 2,200. Yeah, it's going like that. So it goes from about 200,000 to maybe 350,000. So it went up by 150,000 in 100 years. So we should get an answer more like 1,500 this time. Just looking at that graph. Now we got to differentiate this thing. So that was one of them. If we differentiate this, it's easier if you think about a of t. For differentiation purposes, it's easier if you think about it as this thing to the -1 power. Okay. It's easier if you think about it to the -1 power for differentiation purposes. So we know that we just power rule that outside function, so it would be -800,000. And then you make it -2 power. So you would be dividing by this thing squared. -2 power. Then you multiply by the derivative of the inside. So the 1 is gone. This negative exponent will join the 31. So we're going to multiply by the derivative of the inside. So that's how you differentiate exponential functions. Okay, and then that is multiplied by the 31. And then you get the same exponential. Okay, that we forgot our exponent, our t here. Okay. That is the derivative. So I need to evaluate that at 200. I'm expecting to get about 1,500 people per year here. All right, and this is what the politician was really thinking that she'd be able to control. So this is going to be a little bit more complicated to type in here. Okay, -800,000 times -0.014519. And that's a 31. That's what that's supposed to be. Okay. Times 31 times e to the negative 0.014519 and 200. Alright, we're doing that, and then we're dividing all of that by 1 plus 31 e to the negative 0.014519 times 200. Then we got to square that thing. If we get an answer around 1500, I think we did it right. Okay, whatever. It was. I knew it was going to be less than the other one. It's hard to say. Look, just looking at it. But we can. Yeah. So, 27. Oh, I mean that's pretty much 09, right? People, new people per year. Okay. Yeah, significantly less growth rate. That's good. Okay. Don't want things to change too rapidly. That can be unstable. All right, thanks for watching.